Okay, so thank you very much, George, for giving me the opportunity to present this ongoing work. Any comments are welcome. So I'm going to spend some time presenting the context in which this work involves. Then I'm going to present the model itself, a couple of results from the simulations, and some conclusive results. So basically, I'm going to start talk about the bioeconomy. Okay, so for those of you who don't know, bioeconomy encapsulates an economic paradigm which is rooted in the sustainable utilization of renewable biological resources to produce goods and services. And this approach is centered around transforming biological materials into products such as food, feed, bio-based chemicals, and bioenergy. Now, the aim is to transition from traditional fossil-based resources to biologically sourced alternatives. And the bioeconomy touches sectors going from agriculture to industrial processes. It represents the green growth, as you might heard of it, and as well as sustainability. It's one of the pillars of sustainability within the green growth. Now, diverse visions have emerged within the bioeconomy discourse, and those include bioresources, biotechnologies, and agroecology. Now, until now, much of the current research on bio-based supply chains prioritized economic optimization, but there's a pressing need to widen this lens and emphasizing social and environmental performance optimization is equally crucial. Now, our study delves into the strategies that bolster sustainable supply chain management in the bioeconomy. And we wish to see how the transitioning to this sustainable framework necessitates substantial shifts in organizations, which urge them to rethink their supply chain models in accordance with sustainability mandates. Now, in the European Union, the Common Agricultural Policy and the objective of a carbon neutral European Union by 2050 deeply intervene with the bioeconomy's progression. Basically, it serves as a mechanism for propelling rural climate efforts. Now, predominantly, the agriculture and forestry sectors within the bioeconomy not only offer pathways for greenhouse gas emissions reduction, but also in carbon sequestration. As you know, the sectors generate biomass, which that when substituted for fossil-derived materials, curtails emissions in sectors such as energy, manufacturing, and construction. Now, it is essential to note that while the bioeconomy presents opportunities for reducing emissions, it also contributes to GHG emissions, particularly during the production and processing stages. So basically, the focus is more on a fossil-free economy than on a carbon-free one. Now, this nuanced dynamics of indirect mitigation highlights this. For example, while sectors using bio-based materials get credit for reducing emissions, the emissions from the actual production of these materials are allocated to land-based sectors like agriculture and forestry. So in consequence, when agricultural processes produce bio-based materials, their related emissions are charged to the agricultural sector. So this complex interplay underscores the need for a holistic understanding of bioeconomy's environmental impacts and the accurate tracking of emissions reductions. Now, the relationship between the bioeconomy and biodiversity is equally critical, reflecting the potential for the bioeconomy to evolve sustainability, while the bioeconomy can foster biodiversity protection through sustainable resource incentives. Balancing bioeconomy development with conservation goals remains a challenge. For example, the European Union objective to protect biodiversity across a minimum of 30% of its land by 2030 highlights the importance of sustainable land use beyond just strict area protection. Yet, concerns arise with the increased industrial reliance on biomass, particularly from extensive land use or monoculture plantations, which could threaten natural habitats and overall biodiversity. Now, the agri-food systems have at times compromised the genetic resources and nature's regulatory functions. As the significance of bio-based systems grows, so does the urgency to harmonize bioeconomic progression with ecosystem preservation and promotion of landscapes. So basically, after presenting the climate change problem and the biodiversity decline problem, I'm now going to talk about the global challenge, which is feeding an expecting population and improving living standards within the constraints of our planet's finite resources. Now, for this global challenge, the bioeconomy presents a potential solution because it harmonizes economic viability with sustainable production. However, establishing this equilibrium requires careful planning and resource management. While the bioeconomy offers alternatives to fossil resources, its sustainability is not guaranteed. Swapping inputs might not yield broader social benefits or ensure climate mitigation. So basically, the notion of the bioeconomy could potentially only involve the replacement of fossil resources with bio-based alternatives, but it could lack in generating additional ecological and societal advantages and contributing to climate mitigation. Now, if we recognize that market mechanisms fall short of steering this journey towards sustainable development, governmental intervention is then vital to ensure the alignment of ecological, social, economic sustainability criteria. Now, to achieve that alignment, payments for environmental services that you might have heard of are mechanisms where governments incentivize individuals or communities to manage, conserve, or restore ecosystem services like carbon mitigation and biodiversity. Now, by aligning economic goals with conservation, PES systems can ensure economic well-being by accounting for environmental externalities and fostering sustainable resource management. These incentives foster community engagement and promote sustainable resource management, which often results in improved ecosystem health and increased biodiversity. There are also challenges within the implementation of PES, like the true value of ecosystem services, the equitable distribution of payments, and potential unintended consequences of land use conflicts. Now, in the bioeconomic sector, PES encourages sustainable practices and has been vital in afforestation and habitat preservation. Nevertheless, ensuring profitability with ecological conservation in the sector poses challenges. As the bioeconomy grows, integrating PES can guide it towards sustainability, but more research is needed. So payments for environmental services can exert a substantial impact on supply chains, and their intervention introduces a novel dimension by aligning economic incentives with environmental conservation goals. Now, this synchronization sparks shifts in behavior among supply chain participants, which encourage them to adopt more sustainable practices and mitigate negative ecological footprints. Now, the integration of PES can elevate awareness regarding the environmental implications of production processes. This in turn triggers a ripple effect throughout the supply chain, which impacts search decisions, production methodologies, and consumer preferences. We can also say that PES mechanisms can catalyze collaboration among stakeholders, which foster synergies between them, because now they share a goal of environmental preservation. Now, in this paper, our objective is to evaluate the efficacy of PES within a bioeconomic supply chain encompassing both individual producers and cooperatives which have been essential in promoting the bioeconomic activities. So we try to determine the potential of PES to drive reductions in GHG emissions and biodiversity decline within the bioeconomic sector. So the examination hinges on the equilibrium analysis of supply chains operating with network structures. So in the case of decentralized supply chains, which involve multiple decision makers, each participant's behavior requires characterization through a set of equilibrium conditions. And a commonly adopted approach to establish these conditions is the resolution of variational inequality problems. As you know, variational inequality theory functions as a methodology for scrutinizing equilibrium issues. It uses an inequality formulation which encompasses a functional within a convex set. This approach facilitates the analysis of solution uniqueness and existence, and the network equilibrium approach has emerged as a primary method for dissecting supply chain network management, which resulted in a multitude of supply chain network studies. I am among those who have been using this tool for some time now. Now, in this context, the economic equilibrium is defined within a network bioeconomic framework, spanning multiple tiers of the supply chain. And in the realm of network economics, achieving supply chain equilibrium is pivotal for sustainable resource allocation, price stability, and effective coordination across various nodes of a supply chain network. Let me now skip to the model. So we delve into a three-layered bioeconomic industrial network. This network encompasses a cluster of upstream agents or bioeconomic producers, denoted as U, who furnish their products to in-stream agents or cooperatives, represented as I. Subsequently, these in-stream agents distribute the products to downstream agents or retailers, designated as D, who finally sell their products to ultimate consumers, indicated as C. Now, we consider that retailers are responsive to consumer demand, and it is worth noting that the bioeconomic producers possess the choice to directly sell their products to retailers without involving the cooperatives. This network structure adheres to the principle of atomicity within a well-operating market. I'm not going to spend much time on the existence of the cooperatives in this model. Let me just remind, yes?
No, may I ask, what is the specific role played by in-stream agents? Because I see, as you just said, so here the upstream agents can sell directly to retailers. So what is their precise role in the middle?
So basically, the majority of bioeconomic producers are coordinated through cooperatives. But there are also some individual firms who sell directly their products to retailers. So we try to be as realistic as possible within the shape of the market in the bioeconomy. Cooperatives.
Yes. So my question is, what are cooperatives here?
Cooperatives are those who receive products from, they pool the resources of the bioeconomic producers, and then they sell to the retailers.
Okay, thank you.
So, no problem. So basically, once again, cooperatives have been essential in promoting the bioeconomic activities to the farmers, who for some of them have switched to work on bio-based resources for example, energy. Let me now move to the behavior of the producers. So for the bioeconomic producer U, the production is denoted as QU. The non-negative production of output of all bioeconomic producers are encapsulated in a vector capital Q. Producer U is confronted with a production cost function that can be influenced by all outputs, which means that FU is defined with respect to capital Q. Now, this assumption empowers us to operate within the framework of Purno competition. As I said earlier, a bioeconomic producer holds the choice to marketing transaction with a retailer, either via cooperative, which they might have joined previously, or directly. So when bioeconomic producer U engages in trade with retailer D through cooperative I, the associated transaction cost is labeled CUI. The product transaction linked to the trade between bioeconomic producer U and retailer D via cooperative I is denoted QUI. The trade transactions are aggregated to form the vector capital Q. Now, the transaction cost might be influenced by the volume of these transactions, which is represented by CUI function of QUI. As I said earlier and many times before, the bioeconomic producer U has the option to directly transact with retailer D without going through a cooperative, which incurs a direct transaction cost CUD. And the corresponding product transaction is identified as QUD. So in accordance with the flow conservation, we have QU equal to QUI plus QUD, meaning what is produced by the bioeconomic producers is either sold to retailers or sold to the cooperatives who then trade with the retailers. Now, I'm not going to spend too much time on the presentation of the maximization problem because I want to spend time on the variational inequality. Let me just say that within this maximization profit, of course, like any profit equation, you have the revenues minus different costs. 1 minus fee represents a revenue sharing contract between the bioeconomic producer and the cooperative. So basically, we have 1 minus fee times P1I, that stands for the price set by bioeconomic producer U for the product sold to the retailer D through cooperative I. P1U denotes the price directly established by bioeconomic producer U for the product sold to the retailer. The bioeconomic producer and the cooperative engage in a revenue sharing contract, as I said earlier. In addition to the primary objective of profit maximization, we also address the commitment of each bioeconomic producer to mitigate the GHG emissions stemming from the processing and transportation of products. Now, this commitment corresponds to sustainability initiatives and reflects the bioeconomic producers' dedication to combating climate change. Now, the emissions associated with the production of goods by producer U are modeled by the function EU, where EU is function of QU. The emissions resulting from a transaction between bioeconomic producer U and retailer D through cooperative I are denoted as EUI function of QUI. We have the emissions EUD function of QUD, which captures the emissions generated during the transaction and transportation of the product directly to retailer D. And we incorporate this emissions function within a defined structure where we have HUI, HUD, and HU at the beginning, where HU, HUI, HUD represent the emissions generated per unit of product produced and traded. So basically, irrespective of whether a cooperative is involved in the transaction, we differentiate between the emissions produced during bioeconomic activities and those associated with the transaction process. The third requirement for the bioeconomic producer is a commitment to reducing the decline in biodiversity. The biodiversity loss is attributed to the production of goods by each bioeconomic producer U, which is captured by function BU, function of QU. We also have the biodiversity loss arising from the cooperative engagement of a bioeconomic producer U with retailer D through cooperative I, which is described by BUI function of QUI. And we incorporate, once again, predefined damage functions into the analysis. Basically, we have GU, GUI, and GUD, which capture the extent of biodiversity loss associated with each unit of product produced and traded. So, bioeconomic producer U places profit maximization as its first objective, which means a weight of 1. Additionally, we have a non-negative weight alpha, which is assigned to the emissions generated criterion, which ranges between 0 and 1, and another non-negative weight mu, which is assigned to the biodiversity damage criterion, which also ranges between 0 and 1. So basically, the parameter alpha reflects the participants' commitment level in addressing climate change. A value of alpha equals to 0 signifies the producer's indifference towards emissions and a lack of focus on emissions reduction. In contrast, when alpha is equal to 1, it indicates a full dedication to achieving carbon neutrality. When mu is equal to 0, the bioeconomic producer disregards the biodiversity loss, reflecting a scenario where biodiversity is not a factor in their decisions. Where mu is equal to 1, the bioeconomic producer exhibits complete dedication to minimizing the biodiversity loss, fully considering this loss in their profit calculation. So basically, we have this global optimization program, which takes into account the maximization of profits and the minimization of the environmental footprint. And from there, we obtain the variational inequality formulation of this optimization problem. So within the realm of Kurno-Nash competition, bioeconomic producers engage in a non-cooperative stance. Each producer strives to ascertain their optimal production quantity by considering the decisions of their rivals. We assume the production and transaction cost functions of each producer to be continuously differentiable and convex. Each producer independently calculates their optimal production quantity and transactions. And the collective optimality criteria for all bioeconomic producers can be encapsulated in an inequality where each producer choices are optimized considering the actions of their counterparts. We follow lemma 1, which is the optimal criteria for all bioeconomic producers, is to fulfill the following variational inequality under the assumption that the production and handling cost functions for each bioeconomic producer are continuously differentiable and convex. So we now move on to the behavior of the retailers. Now, retailer D allocates a non-negative weight beta to the GHG emissions and assign a weight of 1 to the objective of profit maximization. The parameter beta signifies the retailer dedication to combating climate change. When beta is equal to 0, the retailer is indifferent toward its emissions. When beta is equal to 1, it reflects the retailer's full commitment to achieving carbon neutrality. We also have the parameter nu, which indicates the retailer's commitment level to curbing the biodiversity loss in their trading activities. When nu is equal to 0, the retailer shows no concern for biodiversity loss, reflecting cases where biodiversity does not significantly affect their decisions. When nu is equal to 1, the retailer prioritizes minimizing the biodiversity loss, which then becomes a crucial factor in their decision-making. So this leads us to a multi-criteria decision-making problem, which is formulated as you see on the slide. Basically, the profit maximization and then the minimization of the environmental footprint. From there, we transform this optimization problem into a variational inequality problem. So taking into account the decision made by other retailers, each retailer operates independently within a non-cooperative framework, which adheres to the Kurno-Nash paradigm. The attainment of an equilibrium necessitates the alignment and synchronization of all transactions among the network's decision makers. So the optimality criteria for all the retailers is to fulfill the following variation and inequality under the assumption that the transaction and handling costs for each retailer are continuously differentiable and convex. Now you can observe that in this formulation, we have the parameter gamma, which represents the Lagrange multiplier, which is linked to the constraint, then what is produced by the bioeconomic producers is sold to final consumers. And the equilibrium model internalizes the prices established by both the bioeconomic producers and the retailers. Unlike the bioeconomic producers and the retailers who have an optimization problem, we do not have an optimization of the utility among the consumers. The only thing that interests us is that the consumers satisfy their demand. So we will not have optimality conditions for the consumers. We will only have equilibrium conditions for the consumers. Now, contemporary consumers have a preference for ethical, environmentally friendly, and sustainable products and services. They take into account the transaction costs associated with acquiring the commodity, as well as the emissions generated and biodiversity damages incurred during those transactions when making decisions about the quantity to purchase. So we consider P3C to denote the market consumer's willingness to pay. The demand for the product, denoted as DD, is assumed to be governed by a continuous demand function, which is defined with respect to P3C. Now, consider also a unit transaction cost associated with acquiring the product, and the consumers factor in the pricing determined by the producer. The emissions of greenhouse gases and biodiversity damages related to transactions and purchases are given weights, just as for the bioeconomic producers and the retailers, reflecting the assumption that consumers make decisions based on multiple criteria. So the non-negative weight parameter denoted as eta signifies the significance attributed to the total emissions resulting from consumer transactions. Now, this quantifies the extent to which consumers consider their consumption choices within a demand-driven market economy and their contribution to climate change. When eta is equal to 0, they disregard the climate change resulting from their purchases. When eta is equal to 1, they fully consider the impact of their transactions on the climate change. And finally, we introduce the parameter Z, where Z is equal to 0, customers disregard the biodiversity deterioration, reflecting a scenario where such loss does not influence their decision-making. When Z is equal to 1, this signifies that customers are fully committed to minimizing the biodiversity loss, fully incorporating them into their demand functions. So by integrating those weights into the analysis, we acknowledge the consumer's awareness of their role in addressing climate change and biodiversity reduction and their willingness to prioritize sustainable consumption practices. So we have the equilibrium conditions, which are, as I said earlier, not optimality conditions, but only equilibrium conditions for consumers in a demand market, which are formulated as follows for all retailers and for all producers. So basically, customers opt to buy the product from retailer D if the overall price set by the retailer, encompassing transaction costs, the marginal cost of emissions, and the marginal cost of biodiversity damages linked to the transaction remains below the price customers are willing to pay. In the state of equilibrium, where the demand is satisfied, all the criteria are met, which leads to the formulation of demand markets as a variational inequality problem. So we have the third lemma, which represents the variational inequality problem of the customers. The equilibrium criteria for all the customers is to fulfill the following variational inequality. Now that we have posed the variational inequality for all the tiers of the supply chain, we can formulate the variational inequality problem of the entire supply chain. So for the supply chain to attain equilibrium, the quantity of goods sold by bioeconomic producers to retailers must be in line with the quantity of products purchased by retailers from bioeconomic producers, and so on with the retailers and with the customers. Basically, the supply of one is equal to the demand of the other. The supply of the other is equal to the demand of the third party. We fall on the following proposition. The variational inequality problem of the entire supply chain is the sum of the variational inequality problems formulated independently previously. So the solution to the variational inequality problem subject to the conservation of the flow equation stands as the representation of the equilibrium conditions that govern the supply chain network model with considerations for environmental damages. This solution is derived by aggregating the optimality criteria across all bioeconomic producers, retailers, and customers. And upon resolving the variational inequality to ascertain the prices, the supply chain network attains an equilibrium state guided by the subsequent condition. So for the bioeconomic industrial network, which produces environmental damages, to achieve equilibrium and uphold the flow equation, the marginal cost of net GHG emissions and the marginal cost of net biodiversity damages arising from production and trade must align with the aggregated downstream marginal cost across all channels, while being counterbalanced by the aggregate gaps in upstream marginal cost across all channels. Basically, mathematically, the following expression needs to be verified. Now, I will now dedicate some time to the simulations. So basically, we executed the simulations in Python. We used an algorithm which was employed to solve the variation inequality problem. This algorithm integrated both mathematical optimization techniques and fixed point iterative methods to ascertain the system equilibrium within the network. Now, variables were iteratively updated in line with the model's constraint and the derivatives of the objective function. We aim to converge to an optimal state. Now, in this algorithm, machine learning was integrated via the use of a hyperparameter, which you probably know as a learning rate. Now, this hyperparameter modulated the size of each iterative update by scaling the gradient of the objective function with respect to the parameters. Now, we employed a relatively low learning rate, 0.01, which led to smaller updates, which meant that the optimization was very slow. Now, even though this can give us a really accurate result in optimization, basic gradient descent is prone to slow convergence. So we included the momentum into the optimization procedure. So the momentum parameter was set to 0.9, effectively combining 90% of the prior velocity with 10% of the current gradient for each parameter. So basically, we amplified the optimization direction, and we suppressed oscillations. So we obtained the following results, optimal outputs. So you have the total quantity produced, the total quantity transacted via cooperatives, the total quantities transacted directly with retailers, the emissions during production, the emissions in transactions with cooperatives, the emissions with transactions directly with retailers, and so on. So I'm going to just spend a bit of time to present different results and what they involve. So basically, we obtain, starting from an initial level of production of 1,000, we find an optimized production of 979, which is a decrease of about 2%. So the output between cooperatives and independent production facilities remains constant. Cooperatives contribute 491 units, while individual production facilities add 488 units. Basically, we have half of the production dedicated to by cooperatives and the other half to individual firms. Now, with regard to GHG emissions, we obtained this optimized quantities that reflect the commitment to climate change mitigation, which leads to a total emission of 439. You have to know that initially we consider a 1-to-1 ratio, basically 1 unit produced, 1 unit of emissions. So this quantity marks a decrease of 56% relative to the baseline scenario. So basically, the model effectively curtails GHG emissions with generating only 0.44 emissions units for each unit of production. Now, we also consider the ecological footprint on biodiversity. The biodiversity degradation was at 447, which is a 55% reduction from the initial levels. So each unit of production now causes a biodiversity loss of merely 0.46. Basically, we can assert that a generalized economic decoupling exists between bioeconomic output and environmental damage. So we have been able to separate the increase in production with the increase of the damages to the environment. Now, the optimal price for end user demand, which I said earlier was P3C, or the consumer is willing to pay, was set to be 2.44. And now this pricing allows the bioeconomic producers to offset their expenses. We have a shadow price of 2.48. Now, although approximates to the consumer price, the shadow price is marginally higher. When a shadow price is close to the consumer price, basically it means that the market is efficient. When the shadow price exceeds the consumer's price, this implies suboptimal resource allocation, and there are avenues for policy measures such as subsidies. Basically, governmental bodies should subsidize customers' impact by environmental damages until both costs converge. Now, the parameters alpha, beta, and eta represents the weightings allocated by economic participants to mitigate GHG emissions. So as I said earlier, those values mirror the degree of priority that each agent attributes to carbon emissions. For example, a weight of 0.50 signifies an agent's willingness to cut down emissions by a maximum of 50%. The outcomes reveal that at the points of network equilibrium and social optimum, where both profit maximization and GHG reductions are achieved, retailers and consumers display a modestly risk-averse stance in relation to climate change, which is illustrated by their 0.54 weighting towards lowering emissions. Conversely, bioeconomic production firms with a weight of 0.49 show an attitude that is either risk neutral or mildly risk accepting. The parameters mu, nu, xz denote the importance assigned by different economic actors to the mitigation of adverse impacts on biodiversity. So basically, once again, if you have a 0.5 weight, it means that you aim to reduce biodiversity degradation by 50%. So we obtain a value of 0.51, weighting toward biodiversity preservation from the retailers. On the flip side, entities involved in bioeconomic production with a weight of 0.52 exhibit a slightly heightened level of risk aversion, suggesting more substantial concern for biodiversity losses. Now, the optimal prices for encouraging environmental harm reduction, which are the payments for environmental services, are established at R0.51, which is for the mitigation of climate change, and S0.51, which is for the mitigation of biodiversity decline. Now, in the case of a producer committed to a 49% emissions reduction and subsidized by the government for this effort, the net influence of their economic profit turns out to be minimal. Specifically, the equation where we have alpha times 1 minus R, which is 0.49 times 1 minus 0.51, yields 0.24 per emitted carbon unit. And this amounts to an actual emission reduction effort of 24%. However, as said earlier, the producer successfully attains a 56% emission cut, which means that they outperformed the initial aim by 32.07 percentage points. Similarly, for a producer aiming at a 52% reduction in biodiversity damage and receiving public financial support, S equal to 0.51, the impact on their profitability remains limited. Specifically, mu times 1 minus SI equal to 0.52 times 1 minus 0.51 results in a 0.25 per unit of biodiversity loss, translating into a net effort to reduce biodiversity harm by 25%, yet the producer exceeds this target, achieving a 55% decline in biodiversity damage, or an improved performance by 30.21 percentage points. Now, I'm just going to say very quickly a couple of words on the local and global sensitivity analysis. We find that some effects which are significant at the local scale are diluted on a global scale. So the payments for environmental services from the government do not suffice on their own to achieve such a level of decoupling, maintaining the production as it was initially, while diminishing the environmental footprint. Basically, this is the main message from the sensitivity analysis. Dilution of the effects, and none of the incentives is capable alone to produce such outcomes as the ones that we have obtained. So to achieve a substantial reduction in environmental damages exceeding 50%, which is the case for both GHG emissions and biodiversity decline, a coordinated approach is required. This involves a modest reduction in production as a result of the economic decoupling effects, heightened environmental consciousness among stakeholders, because all the weighting parameters are significant, attain almost 0.50 for all of them, and targeted monetary incentives, which are the PES equal to 0.51 for both GHG emissions and biodiversity decline. Now, these factors, economic decoupling effect, environmental awareness, and targeted monetary incentives from the public authorities are complementary and must be synergistically employed. So it is reasonable to posit that there may be a slight trade-off between U and S, as a lower reduction in BU resulting from a 10% increase in SI can be offset by an increased value of mu relative to alpha. Consequently, we can achieve comparable reductions in environmental damages for both GHG emissions and biodiversity loss. Now, a couple of conclusive remarks. The study provided valuable insights into the intricate sustainability challenges encountered by the bioeconomic supply chain. The findings highlighted the pivotal role of PES as a potent strategy in combating climate change and mitigating biodiversity decline. The application of PES exhibits comparable effectiveness for both individual firms and cooperatives. The incentivization through monetary rewards such as PES lead to substantial reductions of global emissions by 56% and biodiversity decline by 55%, which is achieved through a moderate reduction of production levels, only 2%. Now, these results showcase a noteworthy decoupling between environmental impacts and output, with an emission intensity of 0.44 and a biodiversity intensity of 0.46 when implemented PES. So the outcomes correspond to the pressing need to accommodate a growing global population and embrace land-sparing practices. So the adoption of payments for environmental services emerges as an effective means to accomplish the stipulated goals of the European Union in the context of bioeconomic sustainability. However, and this is what I said shortly through the sensitivity analysis, it becomes evident that while the payments for environmental services play a necessary role, they are insufficient on their own to effect a substantial reduction in the environmental footprint. This is corroborated by the outcomes of the global sensitivity analysis, which indicate that their contribution culminates in a reduction of up to 27% for GHG emissions and 20% for biodiversity loss at most. So basically, in the global sensitivity analysis, PES reduced emissions by 27% and 20% the biodiversity loss. So they do not achieve alone those over 50% decreases. As I said earlier, the reductions stem from the synergistic interplay of multiple factors, each contributing to the optimized outcomes. Now, it is worth noting that our findings align with prior research indicated that PES alone may not offer a complete solution. However, the study suggests that when they are coupled with economic decoupling strategies and heightened environmental awareness, the payments for environmental services present a significant opportunity for public authorities to pursue their environmental objectives. And I'm going to give now the final statement, which is basically the policy implication of our results. PES, or payments for environmental services, can incentivize sustainable resource management practices, yet their efficacy can be optimized when integrated with economic decoupling strategies through production efficiency. Economic decoupling achieved to enhance resource efficiency and shifted production methods is essential to minimize ecological footprints. However, its potential can be fully harnessed when bolstered by both targeted PS interventions and heightened public awareness. The public awareness achievable through education, communication, and engagement nurtures a sense of environmental responsibility among citizens. This, in turn, amplifies the demand for sustainable practices, driving the adoption of economic decoupling measures and magnifying the impact of payments for environmental services. So the interconnectedness of these three components, economic decoupling, environmental awareness, and payments for environmental services, forms a holistic approach whereby the PES stimulate eco-friendly practices, economic decoupling reduces resource consumption, and public awareness cultivates a demand for sustainable solutions. Thank you very much.